What if the most expensive weapon in your country's arsenal could be defeated by an enemy soldier flipping a single power switch? What if a missile worth nearly $1 million could be tricked, blinded, and wasted on a $5,000 inflatable balloon? For decades, this was the dirty secret of modern air warfare. The legacy anti-radiation missile, the Mach 2.9 monster known as the AGM-88 HARM, ruled the skies. Massive, brutal, fast, and quietly, fatally flawed. Now, a new generation has arrived. It does not scream across the sky at twice the speed of sound. It hums, it waits, it thinks, and it hunts in packs of hundreds. This is the story of how a 20-kilogram plastic drone, costing less than a used sedan, is forcing the world's most powerful air defenses into mathematical bankruptcy. Welcome to the swarm era. To understand why swarms matter, you have to understand the weapon they are replacing. The AGM-88 HARM is a brute force masterpiece. Picture a steel cylinder, 13 feet 8 inches long, 10 inches across, weighing 800 pounds at launch. The Yokol solid propellant rocket motor hurls it forward at Mach 2.9, roughly 2,280 kilometers per hour. Its 150-pound warhead, the WA-7B, packs thousands of tungsten alloy cubes that shred a target on detonation. At high altitude, it can strike from over 148 kilometers away. Now picture the operational flow. Step 1. An enemy radar switches on and emits a signal. Step 2. The pilot's radar warning receiver, called an RWR, picks up that emission. Step 3. The missile's passive broadband seeker locks onto the radar's energy. Step 4. The pilot fires. Step 5. The missile rides the enemy's own signal straight back to its source. Simple, beautiful, devastating. But trace that flow carefully and you find the crack. Every single step depends on one assumption. The enemy radar must stay on. Here is the contradiction. A weapon engineered with billion-dollar metallurgy, hypersonic propulsion, and precision seekers can be defeated by a teenager pressing the off button. The moment the radar shuts down, the seeker goes blind. Modern mobile air defenses know this. They emit a brief pulse, then physically relocate within minutes. By the time the HARM arrives at the last known coordinate, the target is gone. GPS and inertial backup help, but the hit probability collapses. Then comes the economics. A single HARM costs $284,000 for older variants, and over $870,000 for the modern ARGM upgrade. The launch platform, whether an F-16CJ, EA-18G Growler, or F-35, costs tens of thousands of dollars per flight hour and risks a human pilot deep inside contested airspace. An enemy can field a $5,000 inflatable decoy with a microwave emitter and force the defender to spend nearly $1 million to kill it. The legacy salvo algorithm tells the pilot to fire down the bearing of the strongest emission. It does not negotiate. It does not loiter. It does not wait. And that brittleness, that one fatal demand for a live enemy signal, is exactly the wall a new architecture was designed to smash through. Enter the AI-driven loitering munition swarm. Forget a single 800-pound missile. Picture a flock of 20-kilogram drones built from carbon fiber reinforced polymer and expanded polypropylene foam. Each carries a payload of 5 to 6 kilograms. Each one has a radar cross-section below 0.1 square meters, meaning enemy X-band and S-band radars struggle even to see them. Each one is electric, powered by lithium polymer batteries running on a 24 to 48 volt architecture with a brushless DC motor so quiet it registers below 60 decibels at 1,500 feet altitude. This is not a missile. This is a thinking machine. Now follow the new operational flow and compare it directly to the legacy chain. Step 1. Launch. Units fire from standardized pneumatic tubes mounted on trucks, ships, or aircraft. One drone every 5 seconds. The solid rocket booster burns for under 2 seconds. Wings deploy via spring tension, and electric propulsion takes over. Step 2. Mesh formation. The drones climb to 500 to 5,000 feet and form a mobile ad hoc network, or MANET. Some assign themselves as sensor nodes, flying high to scan with electro-optical cameras and uncooled long-wave infrared sensors. Others become shooter nodes, hugging terrain at low altitude. The mesh shares data in tiny low-kilobit bursts to stay invisible. Step 3. Hunt. The swarm enters the kill box and executes a geometric search. Convolutional neural networks running on onboard chips that deliver 20 to 100 TOPS, meaning tera operations per second, at under 15 watts of power, parse the video feeds. Targets are scored on a weighted value system. An active early warning radar scores 0.95. A surface-to-air missile launcher scores 0.85. An inert decoy scores below 0.20. The swarm ignores the decoy and hunts the real prize. Step 4. The kill. The mesh allocates targets cooperatively. No overkill, where multiple drones waste themselves on one corpse. No underkill, where a real threat survives. The selected drone dives at 120 to 50 knots and detonates a 5-kilogram high explosive, dual-purpose warhead, which fires an explosively formed penetrator capable of punching through 600 millimeters of rolled steel armor. Now compare. The HARM needed the enemy radar to stay on. The swarm does not. Its dual-mode optical and infrared turret can identify a target visually by shape and heat signature, even when every transmitter is silent. Its passive radio frequency antennae, woven into the wing edges, can still detect emitter bands from 60 to 100 kilometers away when the enemy slips up. When GPS is jammed, the drones switch to optical flow cameras pointing at the ground and MEMS accelerometers for dead reckoning. When the data link is severed, units revert to independent hunter-killer mode. And the price. The HARM costs up to $870,000. A baseline swarm drone costs $30,000. The premium anti-jam variant tops out around $150,000. The cost-exchange ratio inverts completely. An adversary now must spend a $500,000 interceptor to kill an asset worth less than 10% of that price. The HARM industrial base produces dozens of missiles per month through artisanal manufacturing. Swarm production targets 1,000 to 5,000 units per month using injection molding, automated assembly, and 3D printed components. Faster, cheaper, smarter, patient. But all of this means nothing without proof. Does this swarm actually work outside a PowerPoint slide? The proof is already on the record. In August 2023, the U.S. Department of Defense officially announced the Replicator initiative. The mandate was clear. Field thousands of attritable autonomous systems within 8 to 24 months to counter the sheer numerical mass of peer adversaries. Through 2023 and 2024, intensive software prototyping for collaborative autonomy began. Hardware selection favored mature airframes such as Altius 600 and Ghost X, retrofitted with upgraded edge compute modules. The timelines pushed toward the 24-month mark due to friction inside the planning, programming, budgeting, and execution process, known as PPBE. In August 2024, initial limited field testing of early AI visual recognition algorithms ran against mock air defense sites in restricted airspace at proving ground. In late 2024 and early 2025, the Pentagon selected the Enterprise Test Vehicle Program, or ETV, to drive scalable affordable mass. Prototypes from Anduril, Integrated Solutions for Systems, and Leidos entered rigorous physical evaluation. The ETV achieved first flight within roughly 12 months of solicitation. Then came the headline test. On February 18, 2026, Rheinmetall successfully conducted a live-fire demonstration of the FV-0114 loitering munition system at the National Test Center for Unmanned Aerial Systems in Hochstätt, Germany. The test verified 100-kilometer data link ranges, 70-minute flight durations, and simulated swarm attack algorithms against mock-armored targets in a fully GNSS-jammed environment. That last detail is critical. The swarm performed with the GPS signal completely denied. Operational deployment is no longer theoretical. In August 2025, the official Replicator initiative deadline was met. The DoD fielded multiple thousands of all-domain attritable autonomous systems, or ADA-2, to active warfighting commands. In late 2025, the Replicator program was structurally dissolved and functionally absorbed into the newly minted Defense Autonomous Warfare Group, known as DAWG. This shift matters. It moved the entire effort from an experimental pilot program to a permanent institutionalized branch of military procurement. Future timeline is locked in. From mid-2026 through 2027, advanced block software updates will roll out across all DAWG procured swarms. These updates introduce multi-domain orchestration, allowing unmanned surface vessels to pass targeting telemetry seamlessly to airborne loitering munitions. Sea swarms talking to sky swarms. The strategic baseline year is 2027. This is the operational readiness window designed specifically to deter geopolitical modernization milestones by peer competitors in the Indo-Pacific theater. Backing that timeline is a $54 billion Pentagon budget allocation funneled through the Defense Autonomous Warfare Group. The constraints remain real. Crosswinds above 25 to 30 knots degrade accuracy. Desert heat above 45 degrees Celsius forces processors to throttle, blowing the AI. The 6-kilogram warhead cannot crack hardened bunkers. Rare earth magnets and lithium processing tie the supply chain to fragile geopolitics. But the trajectory is fixed. The era of the million-dollar missile chasing. The switched-off radar is ending. The era of the thinking swarm has begun. Here is the question that keeps engineers awake at night. When two opposing swarms meet over the same battlefield, both running independent hunter-killer protocols after their data links are jammed, who actually wins? The side with better algorithms, the side with cheaper drones, or the side with more rare earth magnets in storage? Engineering grit is no longer about thicker armor or hotter rockets. It is about who can iterate faster on a software update at 3 a.m. So tell us in the comments, which next-gen wonder weapon do you want covered next? Hypersonic glide vehicles that outrun every interceptor on Earth, directed energy laser systems burning drones out of the sky, quantum radar that promises to see the invisible? Drop your pick below. If this breakdown gave you a clearer picture of where modern warfare is heading, smash that like button and subscribe. It genuinely helps the channel grow.